Welcome again to this presentation. Today we are starting on question number 11. Question number 11 is saying indicate whether the reaction below are homogeneous or heterogeneous. Explain your answer. Write also the equilibrium expression for the reactions. There's two reactions. Nitrogen gas, which is reacting with hydrogen gas to give the ammonia gas. We have also the reaction for mercury reacting with chloride to give the mercury chloride. Then they are saying, does the following equilibrium expression correspond to homogeneous or heterogeneous equilibrium? So the expression was given. Let's go to the answer. So they are asking to give the expression, the equilibrium expression, and then to indicate whether the reaction are homogeneous or heterogeneous. So we need to understand what is an homogeneous or heterogeneous equilibrium. Let's see what is homogeneous equilibrium. Homogeneous equilibrium or homogeneous equilibria occur when the reactant and the product are in the same phase. That means when you have the product and reactant in the same phase, in that case you have homogeneous equilibrium. Contrary, when you have the reactant and the product which are in different phase, in this case we have heterogeneous equilibrium. For example, if you have the product which are in the gas phase and the reactant are also in gas phase, in this case we have homogeneous equilibria because the reactant and the product are in the same phase. When you have the product in solid phase, as an example, and you have the reactant in gas phase, in this case you have heterogeneous equilibria. For an homogeneous equilibria, in homogeneous equilibria, the reactant and product are in the same phase, while in heterogeneous equilibria, the reactant and the product are in a different phase. Again, what you need to know is that when you have the pure, when you are writing the expression and you have the pure substance, for example, you have a pure solid and pure liquid, in this case, they are given the value of 1. In writing the equilibrium expression, pure substance, pure solid, and pure liquid are given the value of 1. That means in the product, you are not going to see them. If they are reactant, you are not going to see them. If they are the product which are pure, you are not going to see them in the equilibrium expression because they are given a value of 1. So that means when you have the concentration of solid, when you have solid, pure solid, when you have the pure liquid, they are not going to appear in the equilibrium expression because they are going to be given a value of 1. Now let's jump to the answer. Here we have a reaction in which we have nitrogen, which is in a gas, it is a reactant. We have also the hydrogen, which is also in a gas phase. So that means the reactant are in a gas phase. Let's see the product. The product are also in a gas phase. We have the ammonia, which is the product. It is also in a gas phase. That means because the reactant and the product are in the same phase, in this case we have homogeneous equilibrium because the product and the reactant are in the same phase. Now let's write the equilibrium expression. If we're writing the equilibrium expression, so we are taking the ammonia, which is the product, raised to the power of stoichiometric coefficient because we have 2 moles of ammonia, then dividing with the concentration of nitrogen times the concentration of hydrogen, but we have 3 more of hydrogen. This is the equilibrium expression for the reaction. Let's move to the second equation. So here we have the mercury which is in the aqueous phase. We have also the chloride which is the aqueous phase. That means the reactant are in the aqueous phase. Now let's see the product. The product are in solid phase. That means the reactant and the product are in different phase. In this case, when the product and the reactant they are not in the same phase, in this case we have the heterogeneous equilibrium. So remember, when you have the pure solid and the pure liquid, in this case we give the value of 1 in equilibrium expression. That means here in equilibrium expression, so we should take the mercury solid, which is the product, dividing with the reactant, the concentration of mercury 2 plus, times the concentration of chloride aqueous, that is the power stoichiometric coefficient, which is 2. But because we have the mercury chloride, the product, which is in solid, in this case it will be given a value of 1. That's the reason why you can see here the product are given a value of 1, because here we have the concentration of mercury chloride and it is solid. That is the reason why we have given a value of 1. So then let's move to another sub question. For another sub question where the expression was given, here we have the expression for the equilibrium constant, Kc is equal to this one. We have the expression was given. Now they want to know whether this expression comes from a reaction which is homogeneous or heterogeneous. Here, to know whether we have heterogeneous or homogeneous, we should know what are the reactant that we are having and what are the product that we are having. Let's see, we have the reactant. Normally the reactant are supposed to be on the bottom and the product on the top. That is how in the expression here, that means here the numerator. When you have the numerator, it means, for example, here the numerator, these are the product and the reactant on the bottom. That means automatically we have the product. We have this one, this complex as the product, and also we have the chlorine as the product, and the reactant on the denominator, we have the ammonia. The denominator, we have the ammonia as the reactant. So now we are missing with silver and chlorine in the reactant. If you check in the reactant, so we have in the product, you have silver, you can see it. We have also chlorine in the product, right? But if you check in the reactant, you have only the ammonia. So that means we are missing silver and chloride in the reactant. Why are we missing them? That means they are pure solid or pure liquid. So here, because we are missing silver chloride, that means silver chloride is insoluble. It is in solid phase. So that means here the concentration of solid and liquid do not appear in the equilibrium expression, and the silver chloride is insoluble. It is solid. That is the reason why it is not in the equilibrium expression, because it was given the value of 1. Now, if the product then are in aqueous phase, because this one is aqueous, and then the reactant, that means the reactant you have the ammonia and the silver chloride, which is in solid phase, because silver chloride is not coming here because it was given a value of 1. That means that we have an heterogeneous phase. Heterogeneous phase because we have the reactant and the product which are in a different phase. So that is how the reaction is. That means the reaction was silver chloride, which is in solid state, plus ammonia in aqueous state, then which gives the product. It gives this complex plus. So now let's go to question 12. Question 12 is saying, write each expression for K incorporating all constants in the Kp for the following equilibrium reaction. So we are given a different reaction and we need to write the expression for K incorporating all constant, and we need also to indicate the Kp for this listed reaction. Here it's very simple. We need to move to the answer. So if you check for reaction 1, can you go immediately to the reaction 1? If you check for the reaction 1, we have the liquid, here we have the gas, and here we have the solid. So that means here it is in a heterogeneous phase, because we have the solid product and also we have liquid and gas in the reactant. So the reactant and product are in different phase. If you are going to write Kc, that means here we put 1 over concentration of chloride, because the PCA5 is in solid, so and the pure solid and the liquid, we give them the value of 1. Then here we have a Kp, that means when you are expressing Kp, rather than using the concentration, we are going to use the partial pressure, rather than using the concentration. So another question is also the same, so we also use the same logic. So we have the iron, this one, so it is solid state. If you get iron in solid state, and also another one which is not appearing in the equilibrium is also this one, because they are in solid state, we are going to give the value of 1. Then that means in equilibrium expression we will consider only this one and the water molecule and this one. So then for Kc we are going to use the concentration, and for Kp we are going to use the partial pressure. So that is the expression that they were asking. Then another question, that means here for this question, this one will not appear in equilibrium. The calcium carbonate also will not appear in the equilibrium because they are the solid. That means we are remaining only with the concentration of CO2, and then Kp will use the pressure of CO2. So the same as this one also is the same. We have the solid state. This one will not appear in the equilibrium. We will be given a value of 1 because it is in solid state. All the others, they will appear. That means we take this one. We take this one as product times this one. Then we divide with this one. So that is the Kc, which we are going to use the concentration, and then for Kp we are going to use the pressures. Let's move to question 13. Question 13 is saying, in the synthesis of ammonia from nitrogen and hydrogen, we have the Kc, which is equal to this value. The value of Kc was given as 9.6 mole per liter at this temperature, 300 degrees Celsius. Then they are saying, write the relationship between Kc and Kp and calculate Kp for this reaction at this temperature. They have given the reaction. So we know the relation between Kp and Kc. We can move directly to the answer. So what are the given data? We have the reactions. We have also the Kc. We have also the expression. The relationship between Kc and Kp. We know that Kp is equal to Kc times the gas constant. This is the temperature, and this is the change in the number of mole. Of course, if we can calculate the change number of mole, that means we have, for the reactant we have 2 moles, and for the product we have 1 mole from nitrogen plus 3 mole from hydrogen. So that means if you do the difference we see that we get -2 as the change in number of mole. So we can then write the expression, the relationship between the Kc and Kp. In this case, we will be having the Kp, which is equal to Kc times gas constant times temperature -2 as the change in number of mole. We have also the other value, you can replace them. So the temperature should be in Kelvin. So that means the Kelvin we take 273 plus 300 degrees Celsius. That means we get 573 Kelvin. Then the gas constant, we know, then we can replace all the values. By replacing the values, we have here the Kc that was given 9.6. We have also the gas constant. The gas constant here, we know it should be in liter to mole per mole Kelvin. Then here we have the Kelvin, the value of Kelvin, and here we have the change number of mole. So then we get the value. Let's go to question 14. Question 14 is saying predict which system at equilibrium will contain essentially only product, contain essentially only reactant, and contain appreciable amount of both product and reactant. We have here the reaction that was given. They are saying predict which system at equilibrium will contain essentially only product, contain essentially only reactant, and contain appreciable amount of both product and reactant. We have given different reactions. So let's go to the answer. So we need to know when the reaction are contain only the reactant, only the product, and when at equilibrium the reaction will be containing both product and reactant. So in the equilibrium, constant product are in the numerator and reactant are in the denominator. That one we know. So that means when you have a value of Kc greater than 10 power -3, when you have the Kc value which is greater than 10 power 3, if you have the Kc value which is greater than 10 power 3, that means you have more product. Indicate a strong tendency of reactant to form product. That means you will be having the formation of the product. When you have a high value of Kc, that means you have the greater the product, you have more product because the Kc is the product dividing with the reactant. You have the high Kc, that means you have more product, and the product will be likely to form, will be favored when you have the Kc which is greater than 10 power 3. In this case, the equilibrium right to the right, and we are favoring the formation of the product. In this case, we are favoring the formation of the product. You have a high value of Kc, that means you have only the product present at the equilibrium. The high percentage will be the product at the equilibrium if you are having the Kc greater than 10 power 3. So now, when you have a value Kc less than 10 power -3, when you have this value, the Kc is very low. That means if Kc is very low, that means you have less product. That indicates that the ratio of product to reactant at equilibrium is very small. That means reactant do not tend to form the product. So you do have a very small amount of the product, and the equilibrium lie to the left. In this case, when you have a Kc value which is less than 10 power -3, you are favoring the formation of the reactant. You are favoring the formation of reactant. So then if you have the value which is in between, that means all the product and reactant will be present. So if you see this table below, that means when you have the Kc which is less than 10 power -3, mostly you will be having the reactant. Mostly the reactant are present. when you have a value between 10 power negative 3 to 10 power 3, in this case, you have both the reactant, and the product are present. That means you have value in between 10 power negative 3 and 10 power 3. In this case, you have both of the product and the reactant are present in a significant amount. But when you have the Kc value, which is higher than 10 power 3, that means you have product, mostly product are present, and you have a very small count of the reactant. That means here the reaction goes to compression, the reactant giving the product. Here, that is what will be the indicator that, or the reference that will be taking to select whether you have the reactant only, you have the product only, or you have both of the product and reactant. So that means to decide here, we need to decide based on the value of Kc that was given for each reaction. Now this is the reaction that we are having. If you check here the reaction that we are having, we have this one, the first one, and we have the Kc at this temperature, which is equal to 54. So this is in between 10 power negative 3 and 10 power 3. We have also the second one, which is less than 10 power negative 3. You can see this is 10 power negative 18. We have another Kc which is in between. So we have also another Kc which is even higher than 10 power 3. So this is the number 4. So how do we rank them? So if you check for question I and the I, that is question 1 and 3. That is question I. You can see it is having 54. We have also question number 3, which is having 97. That means their Kc is in between 10 power negative 3 and 10 power 3. So it is in the range. So question have equilibrium constant in the range. So the equilibrium mixture will contain both product and the reactant, because they have Kc value which is in between 10 power negative 3 and 10 power 3. In this case, you have both product and reactant are present. Then let's see the equation number 2. So this is this equation. The equation number 2, you can see it is having Kc value which is less than 10 power negative 3. In this case, what do we have? In this case, we have the reactant have a little tendency to form product. That means the system will likely to contain only reactant or a huge amount of reactant. That means the formation of product here, it will be difficult. So then the last equation is the equation number 5. Equation number 5, that you can see it is having the Kc, a very extremely high Kc, which is more than 10 power 3. So in this case here, the reaction will contain only product, because essentially only product will be present because we have a high value of Kc. Now let's go to question 15. It is saying hydrogen and nitrogen react to form ammonia according to the following balanced chemical equation. The equation was given. Values of the equilibrium constant at various temperatures were reported as at 25 degrees Celsius. You have the Kc which is equal to 3.3 times 10 power 8. That means it is higher than 10 power 3. So here again, that means here we mostly have the product. Kc, another Kc that was given, it is at 177. So it's also a high value which is greater than 10 power 3. We have also the Kc value which at 327 degrees Celsius, which is equal to 4.1. So this is in between 10 power 3 and 10 power negative 3. So here this one will contain both product and reactant, and this one they will contain the a huge amount of product. Then they are saying at which temperature do you expect to find the highest proportion of hydrogen and nitrogen in the equilibrium mixture? The nitrogen and hydrogen are in the product, in the reactant. So that means the reactant are the favored when you have less Kc. So then they're asking, assuming that the reaction rate are fast enough so equilibrium is reached quickly, at what temperature will you design a commercial reactor to operate to maximize the yield of ammonia? Ammonia is in the product. Now they're asking at what temperature do you want to say so that you have the high amount of the product. That means the high amount of Kc. Going to the answer, so the hydrogen and nitrogen are the reactant. So I was telling you that we have nitrogen and the hydrogen as reactant. So they are at a high amount. That means high amount of reactant are obtained at a very low Kc value. This is at this temperature. So we have seen that this temperature is the one which has a very low Kc, which is 4.1. So that is where we have the more product. So that's where we have the more nitrogen and the more hydrogen. Then to maximize the yield of ammonia, we need to set the temperature at which you expect to find the highest proportion of ammonia in the equilibrium mixture. This temperature at which, in this case, that is the temperature at which the Kc value are the highest. So the highest Kc value is the one which will give more product. At a very high value of Kc, only product are present at equilibrium, and if we check in the question, this is at 25 degrees Celsius. That is where you have the high value of Kc. At 25 degrees Celsius, you have 3.3 times 10 power 8. That is the high value of Kc. That means the temperature that we will set for our reactor, it will be 25 degrees Celsius. Let's see, question 16 is saying the following diagram represent three different systems, respectively at equilibrium or in same size container. They are asking, without doing any calculation, rank the three systems in order of increasing equilibrium constant Kc. That means the one which has more product is one which has more high value of Kc. So if the volume of the container is 1 liter and each sphere represents 0.1 mole, calculate the Kc for each system. That means each sphere represents each sphere represents 0.5 mole. That means each sphere, this one represents 0.1 mole, right? This is 0.1 mole, this is 0.1 mole, this is 0.1 mole, this is 0.1 mole, 0.1 mole, 0.1 mole, 0.1 mole. That means each sphere represents 0.1 mole. So now let's rank them according to the Kc, rank the three systems in order of increasing equilibrium constant. So how do we proceed? Let's see. Let's start on the first one. So this is the reactant and this is the product. You can see this is the reactant. This one has reactant and the product. So this one. So that means it will not have the high Kc because the reactant and the product are all present. So let's move to the second system. The second system, you have the product. So this is the product. You have only the product in small amount. That means this one will be having the smallest value of Kc because the product only in small amount. So now let's go to this system, the third system. In the third system, you can see the product are have an extremely high amount of the product. 1, 2, 3, 4, 5, 6, 7, 8. That is the product, and only the reactant are 2. So here also that means system number 3 is the one which has the highest value of Kc because it is having more product, followed by the system number 2. System number 2, this is the product. It has 1, 2, 3, 4, 5, 6. 6 moles of the product as compared to the 4 mole of reactant. So that means the system with highest Kc is the one with the system number 3, the one which has the high value of Kc, followed by the system number 1. System number 1 also has it is following system number 3. Then system number 2 is the one which has a smallest value of Kc, because system number 2 is here. You can see it has a small number of mole of the product. Only 0.1 mole of product are there, so it will be having a very small amount of Kc. Now they are saying if the volume of the container is 1 liter and each sphere represents 0.1, calculate Kc for each system. So we take the concentration of the reactant dividing with the concentration of taking the concentration of the product dividing with the concentration of reactant to calculate the Kc. So if you can check here, we have the 0.1 mole, so that is the Kc1. We have 0.1 mole times 6, because we have 6 spheres in the product. That is the Kc1. So we have 1, 2, 3, 4, 5, 6. That means 6 spheres in the product. If we take a mole dividing with 1 liter, in this case we have the concentration. Here also we take the moles, then times the number of, that means we have 0.1 mole per sphere times the number of spheres in the reactant, then we divide with the volume so that we get the concentration. Let's move to the second. In the second, we have only one sphere in the product. That means we try 0.1 to get the total number of mole for the product, dividing with the volume. Then we divide 9 spheres in the reactant. Then we have 0.1 mole times 9 spheres, so that we get the total moles, dividing with 1 liter, so that we get the concentration. Then the last one, we have Kc3. So we have 8 spheres in the product, and we have 2 spheres in the reactant. Then here also we have the values. So these are the values of Kc that we're asked to calculate. So question number 17, they are saying for the reaction was given, the Kp at this temperature is equal to this one, and Kp at 700 Kelvin is equal to 54. They are asking is the formation of HI favored at the high temperature. Here we need to check what is the value of Kp at the highest temperature. Highest temperature, the HI is the product, so that means here the HI, we have the product, and they're asking when the product are favored, is it at the high temperature or low temperature? And if you check this product, we need to check the Kp. When we have a Kp, a high Kp, that means we will favor the formation of the product. A low Kp favor the formation of reactant. So that means to check, we check whether at the high temperature if we have the high value of Kp. So if the high temperature, so that means we have two temperatures. We have 298 Kelvin. We have also 700 Kelvin. Can you see that the K at 700 Kelvin is 54, and K at low temperature we have 294. That means at low temperature, that is where we have a high value of Kp. So at low temperature, that is where you have the high value of Kp, meaning more product. Then here at the high temperature, that is where we have a low value of Kp, that means less product. So that means the formation of HI is not favored at the high temperature. So the formation of HI is not favored at the high temperature because at the high temperature the value of Kc is small as compared to the one obtained at low temperature. So the small value of Kc at the high temperature indicate that the product amount are not favored, and it indicates that the amount of product is very small at the high temperature. The more Kc value, the more product are present at the equilibrium. That's what you need to know. When you have the high value of Kc, you have the product, the more the product. When you have the low value of Kp, you have the less product. So question number 18, they are saying you work with the following system. You have 2x gas, which gives y gas. Calculate y at equilibrium if k is equal to 10 and y is equal to 3x. So here it's only to do the mathematical expression. That means the k, here k will be equal to y, which is the product dividing with the reactant to x raised to the power stoichiometric coefficient. So the k was given, k is 10, so equal to 3x, y is equal to 3x. Here we have the also 2x squared, 10 equal to 3x over 4x squared. So if we continue, then you can multiply. You can multiply this 10 with 4x squared, then you get 40x squared, which is equal to 3x. Then we get 40x squared over x. We are taking this x to other side, then we get 3. Here then you get this one, 40x equal to 3. We have x equal to 3 over 40. Then we have a x. After having the x, then they are asking calculate the y at equilibrium. So then calculate y at equilibrium if k is equal to 10 and y is equal to 3x. So after equilibrium, you have y minus 3x is equal to 3 times this one, then you get the value of y. So after getting x, then we have the at equilibrium, we know y is equal to 3x, then we take y is equal to 3x, 3 times x, then you get this value.